I hate doing this. I will. I'm not even ready yet. Y'all have me all like messed up. Here I was rushing to make the test. What? I don't know. It's done that a couple times, so I don't know if it's like, I don't know, shorten out or something. I don't know. I don't care. All right. Can y'all see? Y'all good? I'm sorry, what?
Are you going to go over the check here on this one? No, I just know.
Do I really have to?
No.
What do you want to know about it? What'd you get? Fails to reject. So you should have got a p-value of 0.275.
I'm just having trouble interpreting, like that's not on there, but interpreting p-values, I just don't know how to word it.
Okay, we're going to go over that,
Okay.
and that's definitely in your review as well. So the highlights that you have, okay?
Okay.
All right. So study designs that involve making two observations on the same individual or one observation on each of two similar, I don't like what this says, individuals yield paired data. We wouldn't have had time to finish it. Y'all should have told me. I don't know why I don't have all of it. When paired data result from measuring the same quantitative variable twice, we can make comparisons by analyzing the differences in each pair. Now, real fast, if I don't get these finished, we'll just push everything back, like I said, okay? So if we don't finish these notes, like we might take some time, not, you know what I'm saying? If it takes too long, then we'll just cut it off and be done. But then I'll finish the notes and do the review tomorrow and then push everything back Monday, Tuesday. Got it? What? Friday of next week. So I just got to get that test in before then and try to give it, like, if we have issues, try to make sure that you have time to fix that before I put it in the grade book. All right. And I may split this test. It doesn't change your average. So understand that. So I think I'm supposed to have 4 major grades. Right now, I think you only have 2. I think you have chapter 7 and chapter 8. And so chapter 9 would only give you 3. But if I put it in as 2 separate ones, which is the same exact thing as if I put it in as 1, y'all understand that, right? Then it just don't freak out about it. So try to do good on both of them. But it averages out to the same thing. So I just want you to be able to have those. All right.
Wait, what do you mean 2 separate grades?
Are you so loud for? So you're okay. Putting it in as like chapter 9 multiple choice and then chapter 9 free response, 2 separate grades instead of averaging them together.
Okay, gotcha. That makes sense.
Okay. Or maybe y'all might like this better, taking your highest grade and making it count twice. Like your highest test grade.
That sounds good.
Ain't nobody ask you? Everybody good? I'll have to see. I think I have to have 4 in there. So I think that may be what I do. That'll help you guys out a little bit too. Okay. All right. If the conditions for inference are met, We can use a one sample T procedure. To perform inference about the mean difference. And that's mu sub D. These methods are sometimes called paired T procedures. An example should help illustrate what we mean. So is caffeine dependence real? Paired data and one sample T procedures. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took placebo. Hold on, I'm on the wrong line, sorry. During a 1-day period, subjects took capsules containing their normal caffeine intake. I apologize, y'all. And during another 2-day period, this is the line I thought I was on. They took capsules containing placebo capsules. Okay. The order in which the subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. All right. The table below contains data on the subject scores on the depression test. Higher scores show more symptoms of depression. For each subject, we calculated the difference in test scores following each of the 2 treatments. And that would be placebo minus caffeine We chose this order of subtraction to get mostly positive values. Everybody good? All right. So there's your chart. Why did researchers randomly assign the order in which subjects received placebo and caffeine? Why do they do that? I don't understand. What, sorry, too much movement going on. What do you mean?
Well, if they knew which order, I don't remember the term, but if they knew which order they had received the treatment, they would react differently.
Okay. It's not really, in this case, it's not a bias. It's what? Remember, bias is more like, it is, but it's not. Bias deals more with like when you're given surveys and stuff like that. Okay. So like undercoverage, non-response, those are more biased. What is this going to be? Why did they randomly assign the order? Why do you keep saying bias? Like what, give me an example of what you're talking about.
If they knew they were receiving placebo fraction,
Okay. What else? It's another reason they randomize it. Now remember, they're probably not going to know anyway, because in an experiment, you want them to be blind, right? They don't know if they're getting the placebo or the caffeine. It's going to look exactly the same. So in that case, that's one thing they did. They controlled, and that's what you're talking about, the controls. So why did they randomize it? It is to decrease confounding factors, so other variables that could cause this, okay? So we wanted to make sure the subjects were responding to the treatment and not other variables. Okay, so here's going to be an example, and this is what they say in your book, and this is, you guys can go back and read it, it's in there. It said, suppose that caffeine were given to all the subjects during the first 2-day period. What if the weather were nicer on these 2 days than during the second 2-day period when all the subjects were given a placebo? Researchers wouldn't be able to tell if a large increase in the mean depression score is due to the difference in weather or due to the treatments. Random assignment of the caffeine and placebo to the 2 time periods in the experiment should help ensure that no other variable, like weather, is systematically affecting subjects' responses. So they just gave you an example. This is the answer, and then they give you an example. You guys think about it. How do you feel on rainy days? Right. You see what I'm saying? On days that you slept like you didn't get enough sleep, that's why you want the caffeine, is because you feel like you need to be pepped up. Okay. Did you? Good. Carry out a test to investigate the researcher's question. So we're going to follow that 4-step process, and the first thing that we're going to do is state what goes in our state. Your null and your alternate. What's your parameter? Nope, it's not going to be 2, because what did they do to them? Look at your chart. What did they do?
Oh, subtract.
They subtracted them. So we're looking for mean difference. Remember, I write that mu sub d, right? All right. Well, what would our null hypothesis be?
Would it be 0?
Why?
Because they're seeing if there's a difference at all.
Yeah, they're looking to see if there is a difference. If we subtract and we get 0, there's no difference, okay? So then think about what they did. Why did they do placebo minus caffeine? To get positive numbers, right? So what does that mean this has to be? Greater than 0. Okay, and if you have to write that on there because it's positive numbers, that's why, okay? All right, so then,
Wait, hold on.
okay,
Why wouldn't it be any value that's not 0? And if there's a difference,
because we want to make sure that the stuff worked. So we want
Oh.
those positive values.
all right.
Yeah.
gotcha.
That it did cause a difference, not that it did not. Okay. All right. So this is the true mean difference. In depression, blah, 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 blah. What else do we need in the state? Which is good. Unless they specify otherwise, use 0.05. All right. All right. So in our plan, we're going to do a paired t-test. Why is it a paired t-test? There's 2 things. Yeah, we're looking for the difference. Okay. What else do we need? It's T. So what are we doing?
You gotta test the conditions.
Uh-huh. And those are?
Random 2%.
Is it random? How is it random? Say what? It does. Tell me where it says it. Okay, so that's not where it's randomized, right? It's 11 volunteers, so that's not good. The order they got the medicine. Order of treatment. So watch that, okay? So were they randomized volunteers or they randomly selected? No, they weren't. They were volunteers, so they came in. But again, how did they fix that? Okay. All right, so that one's good. What do we check now? 10%. How many people? What are we doing? Is this sneaky? What did I just say?
Would it be? Would it be? This says 11 people,
Did we sample?
but it's 2.
Did we sample? No, we didn't take a sample, right? So this doesn't count in this. So on your 10%, and I know it's weird because we haven't done it. So we aren't sampling. We aren't sampling. So unnecessary. When else is it unnecessary for the 10%? Okay, one more time. Something else. Infinite or think about drawing cards. You replace them. Okay, so you don't always have to do the 10%. Okay, so there's 3 scenarios where you don't have to do the 10% rule. What's your next thing you got to do? Normal or large counts. Remember, they put the normal on there because if the large count fails, you have to make sure that it's normal by graphing, right? All right, so what do we think?
Wouldn't be large sample amount.
I meant to say sample. Sorry, thank you. You are correct. Sorry about that. What is it?
And it's 11 and 30.
N is 11, right? Which is
Not greater than 2.
not greater than 30. It's less than 30. So we need to what? What are we going to graph? Yeah, the differences. And I'm going to go ahead and tell you that they are going to look like something like this. So the box plot, this is exactly what it says. The box plot shows some right skewness, but no outliers. So it's okay. So with no outliers or strong skew, we're going to be fairly accurate. And I don't really like this. I would go more on, like, I guess if it's like super next to it, you know what I'm saying? Like it's all the way down there. But I would go more on outliers than anything. And I don't think they're going to give you anything within your free response that you're going to have to stop. Does that make sense? Now, if it's multiple choice, they might be like, why can't you do this? And one of the multiple choice answers might be it's strong skew or something like that. Okay, so no outliers or strong skew. So you're going to assume normality. All right. So because we have data, I'm going to go ahead and give you everything that you need to know. If you have a question about how I got that, we'll talk in a little bit. Put it in your calculator, do your t-test from your data, okay? We don't have to do that right now. I don't want you to have to put that in there. So I'm going to go ahead and tell you that your t is 3.53. Your degrees of freedom is 11 minus 1 or 10. And you find these p-values the same. It's still that one set of numbers. So it's the same thing we've been doing. There's nothing any different. And then your p-value is going to be 0.0027.
So on these, we found the p-value the exact same way.
Yes, the same way we've been doing it. So if you have to put your data in and you do your t-test, you guys know how to do that in your calculator, do your t-test and all of that. Same exact way. Normal, all of those fall within this differences. So we're not doing two samples. We're still doing one sample. So everything's the same. Now, next chapter, we're going to have two samples. Okay. So this is the difference in one sample. Everybody understand? We're only taking one sample of 11 people. All right. So then conclude. We're going to test our p-value to our alpha. What do we find? Sorry. Say what? Why? And you said do what now? What'd you say do? And in context? Evidence that and then make sure that when you're doing this, you put what they did, placebo minus caffeine. Is what? Which means that it is positive. Good. Any questions? All right, on this next part, we're going to skip quite a bit of the stuff. We're going to write it out, but we don't have to write all the rest of it. You'll see what I'm saying in a minute. Give me a second. Sorry, it was the boss. All right, a few follow-up comments about the example are in order. I'll move it in a minute so you can see it. I'm sorry. We could have calculated the test statistic. In the example using the formula, T equals the sample mean of the difference minus mu sub 0 over the standard deviation of the difference square root of n. That's the same formula we've been using. This is if we do it by hand. Those numbers would be 7.364 minus 0 over 6.918 over square root of 11, which gives us 3.53. Okay, so if you want to know where I got all those numbers from, T, there it is. And obtain the p-value. Using table Beer technology, just like we've done on every other example. It says check with your teacher on whether the calculator only method is acceptable. And I told you it is as long as you write everything down, okay? So be sure to report the degrees of freedom. With any T procedure, even if your technology does not. All right, so I lied to you. All of this we're doing is the next section. After the next, check your understanding. So we're going to skip some stuff. The subjects in this experiment were not chosen at random. From the population of caffeine-dependent individuals. As a result, we can't generalize our findings to all caffeine-dependent people, only the people like the ones who took part in this experiment. Okay. Again, because you didn't random sample from the entire population, you can't say a conclusion about the entire population. That's all that says. Because researchers randomly assign the treatments, they can make an inference about cause and effect. I don't know if you guys remember that chart from way back when, the cause and effect chart. The data from this experiment provide convincing evidence that depriving caffeine-dependent subjects like these of that caffeine causes an average increase in depression scores. Until now, we have only used one sample T procedures. In settings involving random sampling. The paired data in the caffeine example came from a matched pairs experiment. In which each subject received both treatments in a random order. A coin toss or some other chance process was used to carry out the random assignment. What's another method of random assignment? Yeah, names out of a hat, stuff like that. So all they're doing in these paragraphs is bringing you back to like chapters 1, 2, 3, and 4. Y'all understand what I'm saying? So they're reminding you about matched pairs and things like that. Why is it legitimate to use a T distribution? To perform inference about the parameter mu. In a randomized experiment. The answer to that question, we'll have to wait until the next chapter. And again, you're practically doing the same thing. You guys remember when we did like Aaron and Pete's Jeep tours? So we did Aaron first. We did Pete first, and then in the next chapter, we started adding Aaron into it. It's kind of going to happen the same way, okay? All right. So the check your understanding says refer to the data exploration from chapter 4 on page 257. We're not going back there. Do these data give convincing evidence that the alpha equals 0.05 significance that filling tires with nitrogen instead of air decreases pressure loss? All right. So when we were talking about this is the same thing. It's going to be that difference. Let's see. Let's think about. I'll just go back to it. 257. Most automobile tires are inflated with compressed air, which consists of about 78% nitrogen. Aircraft tires are filled with pure nitrogen, which is safer than in air in case of a fire. Could filling automobile tires with nitrogen improve safety, performance, or both? Consumers Union designed a study to test whether nitrogen-filled tires would maintain pressure better than air-filled. They obtained 2 tires from each of several brands and then filled 1 tire in each pair with air and 1 with nitrogen. All tires were inflated to a pressure of 30 pounds per square inch and then placed outside for a year, so 30 pounds per square inch. At the end of the year, Consumers Union measured the pressure in each tire, the amount of pressure lost in pounds per inch during the year where air-filled and nitrogen-filled tires of each brand is shown in the table below. All right. So what they want you to do is find the difference. This is a lot of data. It's, how many did we say? Tires? I don't know. It's a lot of them. I think there's 30 of them or something like that. And I don't want y'all to have to put that in, okay? So it's the same thing that they did. They found the difference and then they did the T procedures, okay? So I'm not going to do all this. If you guys want to look back, that's perfectly fine. I will tell you that T was 5.80. The P value that they got was super, super small. So they approximated it to 0. So they tested the P value against alpha. The P value was 0. Alpha was bigger, so they rejected H sub O. And then just to throw it out there, H sub O was that mean difference again, was 0. There was no difference in the air. And then we wanted the difference greater than 0. And what they were doing was air minus nitrogen. So again, all the work is exactly the same. I just don't want you to sit here and spend all your day trying to type that in or whatever. Okay. All right. This is the section where we're not doing a whole bunch, when we get to determining sample size and stuff like that. Using tests wisely, significance tests are widely used in reporting the results. Of research in many fields. New drugs require significant evidence. Of effectiveness and safety. Courts ask about statistical significance. In hearing discrimination cases. Marketers want to know whether a new ad campaign significantly outperforms the old one. And medical researchers want to know whether a new therapy performs significantly better. In all these uses, statistical significance is valued because it points to an effect that is unlikely to occur simply by chance. So carrying out a significance test is often quite simple. Especially if you use technology. Using tests wisely is not so simple. Here are some points to keep in mind when using or interpreting significance tests. All right, determining sample size. How large a sample should researchers take when they plan to carry out a significance test? The answer depends on 3 factors. The first one is significance level. Effect size. And the desired power of the test. Here are the questions that researchers must answer to decide how many observations they need. The first one is significance level. So how much error could they handle? Remember, what your significance level is the probability of a what? Alpha is the probability of which error? Oh, you better know that. Type 1 error. So that's what they're, how much error will they let loose? Okay, so your significance level. The second one, we're going to skip all that stuff in between, is the effect size. This is the one that I want to go over. The effect size is how large a difference between the null parameter and the actual parameter value. Is important for us to detect. This is the one, just make sure you know what that means, the effect size, and you're going to go over it again. All right. And then the power. So let's illustrate typical answers to these questions.
Is the power like
We're going to go over it in just a minute. It's just basically how strong we want it to be. Okay. Let's illustrate typical answers to the questions using an example. So this example is going to help you understand that a little bit more, okay? All right. So can a 6-month exercise program increase the total body bone mineral content TBBMC, because you guys definitely needed to know that, right? Of young women. A team of researchers is planning a study to examine this question. The researchers would like to perform a test of your null hypothesis being mu equals 0, and your alternate being mu is greater than 0. Mu is the true mean percent change in the TBBMC due to the exercise program. To decide how many subjects they should include in their study, researchers began by answering the 3 questions above. All right, so significance level. The researchers decide that alpha equals 0.05 gives enough protection. Against declaring that the exercise program increases bone mineral content. When it really doesn't. All right, so think about it. When we have an alpha of 0.05, what kind of confidence interval, like what's our percent confidence interval we're looking at? How confident are we? 95%. Now, we can drop that down to that 0.10 or drop the alpha up, pull the alpha up to 0.10. But what does that drop our confidence to? 90%. Or We can decrease alpha to 0.01, which makes our confidence what? But what's happening in each of those? Why would you use 0.05 instead of the two of them?
On how close you really want your interval.
Yeah, your 90% will give you a tinier interval, right? Right? But with less accuracy. So the chances of a type 1 error are going to happen are a little bit stronger with the 10, okay? If we drop it at 0.01, then the chance of a type 1 error happening is really slim, but our range is going to be huge. So we might not be right at the true mean. Does that make sense? So 0.05 gives you that good happy medium, okay? So that's why they usually choose 0.05. All right. So then effect size. A mean increase in TBBMC of 1% would be important to detect. Then I hold off and I will talk more about that effect size because we really haven't talked about that much. But I'm going to talk more about it, especially in our review, because you have a couple questions that deal with that effect size. Okay, so I want to make sure you know it right for your test. For the power, the researchers want probability at least a 0.9 that I test at the chosen significance level remember sig level is alpha, will reject H sub O when the truth is that mu equals 1. Remember, H sub O is that mu is 0. Say it again. We're gonna talk more about each of these as we do our test review. So don't stress out, just put it in there. All right. So this last little part that I'm going to do today, and then we'll stop, kind of helps you that. The following activity gives you a chance to investigate. I know y'all are tired, I'm sorry. I'm almost done. A chance to investigate the sample size needed to achieve a power of 0.9. In the bone mineral content study. So it says in this activity, you will use the statistical power applet in the book's website to determine the sample size needed for the exercise study. Based on the results of our previous study, researchers are willing to assume that the population standard deviation is 2 for the percent change in TBBMC over the 6-month period. We'll start by seeing whether or not 25 subjects are enough. So then they go through all of that, determining whether it is enough. So here's the summary of that and why they're doing the applet. So here's a summary of influences on how large a sample do I need from the activity. So these are the things that you really need to make sure that you know. If you insist on a smaller significance level, such as 1%, so alpha 0.01, rather than 5%, 0.05, you have to take a larger sample. Why is that the case? What did I tell you? What does that 1% change your confidence to? What does a 99% confidence do to your interval? Makes it wider. So how do we decrease that variability? Larger sample. So everybody understand that. You know that, you just don't know it in the context of this problem, okay? So now you know it. A smaller significance level requires a stronger evidence to reject the null hypothesis. If you insist on a higher power, such as 0.99 rather than 0.90, you also need a larger sample. A higher power gives a better chance of detecting a difference when it really exists. It's the opposite of this. Your significance level is 5%, your power is going to be 95%. Okay, does that make sense? So it's basically the same thing. All right, at any significance level and desired power, detecting a small difference between the null and the alternative parameter values requires a larger sample than detecting a large difference. So we want the largest possible sample that we can get. Okay. So last paragraph and then we'll stop. Okay. Actually, we'll just stop right there. We'll finish this up tomorrow. All right, so what do we have? 1, 2, 3 pages. We'll do that and then we'll do our review. I will post your multiple choice for tomorrow. You do not have any homework tonight. I will post your multiple choice for tomorrow. You're right, everybody was on Zoom. All right, sometimes. I'm gonna go ahead and stop sharing, stop recording.